Okay, so hello everyone. I'm Pallavi. I used to be a postdoc at the University of Leeds. Right now, I'm a visiting researcher. I left back to India just this July, I think July it was, um, because the pandemic and whatnot. So I'm here back in India with my family, and I'll be soon joining as a faculty at an institute over here. But I thought this would be a good opportunity to engage with University of Leeds again. Okay, let me now start with my talk. So I'm going to start screen sharing again. So I'm going to talk about dynamos and magnetic reconnection. These are two processes you encounter in the field of astrophysics, particularly fluid dynamics aspect of astrophysics. And um, this is important because, particularly in astrophysics, because largely the universe is made of plasma, so you encounter these processes quite often. So this will be one flavor of fluid dynamics that I'll be presenting to you, apart from everybody else. And I don't know if you have already done magnetohydrodynamics, but I think I will assume that you have not done, because it's perhaps a little too early for you to have gotten into it yet. So, in fact, I'll be trying to introduce the induction equation. So here's the outline of the talk. So I'll first show you some astrophysical observations involving magnetic fields, to just give you an idea of why at all we are doing all of these studies and research on this topic. Then I will introduce the MHT equations to you, out of which 2 out of 3 you would know, and the third one is the main one. Then I'll be talking about turbulent dynamos. Turbulence comes into this, yes, so it plays a big role, so I'll be talking about that. Then what are large-scale dynamos? Why do we care about them? What are the outstanding problems? What are the recent progress? Then the second process that I would like to talk about, the magnetic reconnection, and then how it has a role to play in the context of MHD turbulence. Then I thought, okay, I included open problems in reconnection, which I can recount to you if you're interested. Then I'll summarize. Oops, sorry. Yeah. So these are some pictures of observations. So on the left-hand side, can you see my cursor? Let me know if you can't. Okay. So on the left, you have basically optical. Hello, did somebody say something?
It was just to say we can't see the cursor, or I can't see it.
Can you see it now?
No.
The pointer? I have been
Yes.
able to.
Yes, can see it now.
Okay. Okay. Great. Thanks, Rose. So, yes, on the left, this is an optical image of the sun, and you can see these black spots. They are basically called sunspots. So these are regions where you have intense magnetic fields, and because of the presence of intense magnetic fields, it inhibits the transport of heat in those regions. So temperature becomes lower, and thus they come across to be dark spots. And here in this panel, basically it's a magnetogram that shows the magnetic fields on the surface of the sun. And what you see in black and white are the opposite poles of the magnetic field. So you can see that they're concentrated wherever you have the sunspots. So you can see them pretty clearly. And what you see in this third panel is basically longitudinally averaged radial magnetic field, which has been plotted over many years. and you can see clearly some kind of cyclic activity, periodic nature to the magnetic field emergence, I mean magnetic field evolution, right? So there's clearly some kind of, large order, uh, large scale order in the nature of the magnetic field evolves, right? This is the sun, but also as an example, we have um, galaxies. So here I have M81 spiral galaxy where you can see these radio contours. In fact, the radio contours are already like the signature of the presence of magnetic fields. Then further, you may be able to see also, it's kind of faint, but you can see like these yellow lines, which are basically vectors plotted for the magnetic field. And you can see that from the alignment that these are aligned on pretty large scale. These are coherent magnets, they're aligned along the spiral arm even. So these are like really big, large coherent magnetic fields. And this is not the only galaxy that hosts them. There are a lot of spiral galaxies that basically you see it all the time, that there are magnetic fields in galaxies, right? So this is not only in case of, objects like sun and galaxies, but also bigger, much bigger objects like, galaxy clusters. So this is the Hydra galaxy cluster. So in optical, you can see these are many, many galaxies in the, in the field of view. And if you look at the same thing in radio, you see actually these jet-like structures. These are basically jets, of course, and there's this faint radio emission also. So it's actually one object. They are all gravitationally bound to each other. So it's basically the galaxy cluster, the biggest object in the universe. So even here, with this radio signature, we do see magnetic fields, coherent magnetic fields. So that forms the motivation for like trying to understand where do these magnetic fields come from. Of course, there are also interesting phenomena that happen on the sun. For example, there are these solar flares, right? So what's going on is that the sun tends to spew plasma once in a while from the surface of the sun. So here, this kind of rope that you see, it's basically magnetic field lines, sometimes called magnetic flux tubes, carrying plasma along with it from the surface of the sun. And what happens is eventually it pinches off and the plasma gets thrown out. So there's like a really nice video which kind of schematically shows that. So I wanted to show you the video, so let me try to do this funny thing of going back and forth. Here. So that's your magnetic field lines which emerge out of the sun, and they kind of pinch off over here. The pinching off is happening due to what's known as magnetic reconnection. And then those magnetic field lines come and interact with the magnetic field of the Earth and again reconnect to form a bow shock, and then the plasma it's carrying along with it travels towards the Earth, and then you actually get these aurorae, this beautiful stuff that you see around the poles, right? So all this is happening because the sun is sending out plasma, and that's going and interacting with the magnetic field on Earth, and all of that is happening because reconnection is taking place, right? So let me come back to my slides over here. in the full screen over there, but I don't know why it didn't work that time. Okay, so the question now is, why should we care about these magnetic fields? So I've already told you this earlier, that it's plasma universe out there. 95% of the universe is plasma, even though around our Earth it seems like it's empty space. But if you, we are situated like, towards the outside of this, like towards outwards to the very end of Milky Way galaxy. But if you kind of travel into the galaxy, you will basically see plasma everywhere. So it's important to understand what's going on. Then magnetic fields to give render the plasma with certain properties. They tend to give fluid-like properties. So that's why you can do, hydrodynamics and fluid dynamics on top of, to understand these objects and what's going on. They can control star formation. They can help trace galaxy formation. These are important subfields of study in astrophysics. Then crucially, like I kept telling you, that if you see radio signal from basically radio uh, observations from certain astrophysical objects, it means it's probably hosting magnetic fields. That's because there's something called synchrotron emission that comes out of, these charged particles gyrating around the magnetic field. So that emission is in the radio band, and that enables sometimes for us to see objects which you cannot see in optical because they are really far away. So that magnetic fields enable us to see objects. Then the final argument is that basically, if you were to do your physics of understanding how the system evolves, you have to take into consideration the magnetic fields also, because they affect the dynamics being significant in strength. Okay, now we will go on to the first topic, turbulent dynamos. So they wanted to understand the origin of magnetic fields, right? So like we see all these large coherent magnetic fields. Where do they come from? What maintains them? So the answer, the more popular and more successful paradigm is that of turbulent dynamos. So what do? They convert part of the kinetic energy of the turbulent motions in the plasma to magnetic energy. So this is essentially the definition of dynamo, right? What does dynamo do? It converts kinetic energy to magnetic energy. How does it do so? We'll see that later. There is a so also already at this point, I just want to tell you there's something known as large scale dynamos and there are small scale dynamos. The classification is based on the fact that how coherent do these how coherent do these magnetic fields come out to be from the dynamo process. So the large scale dynamo makes like really coherent large magnetic fields, whereas the small scale dynamo is going to make small fields. Okay, so this is a typical spectrum plot. So if I were to plot the wave number here and magnetic energy here across different scales, the large fields would be, I mean, this is the technical definition, that if you have turbulence and the energy injection scale is over here, then the large scales are basically scales larger than the energy injection scales, and small are those smaller than the energy injection scale, right? So that is a technical definition that you need to keep in mind. Okay, before I go on to tell you more about dynamos, I thought it's important at this point to introduce the induction equation. So I've been talking about the magnetic field. So I have to tell you what is the equation for it, dynamical equation for it. So what I have here is the Maxwell-Ampere's law, and here we have the Ohm's law. This one you would have encountered electromagnetism, you know, all your Maxwell's laws and so on. Law is probably closer. I mean, yeah, I mean, there's like a more generalized version of the Ohm's law, but this is like the simplest version. So if you were to eliminate the current density, this is electric field, magnetic field, and the velocity here. And this is the current density. So if you were to eliminate the current density from these two, then you arrive upon this equation. Okay. So there is this ddt term for the electric field, and then rest of them. Turns out that this term, which is called the displacement current term, right? That goes away for non-relativistic plasma. So, which is typically most of the plasma is non-relativistic unless you are like in very high energy regime. So, for galaxies and sun, we're going to basically ignore this. We drop this out. And then only this remains. So you have electric field in terms of magnetic field and the velocity. So then you can put that back into, okay, yeah, you can substitute that into the Faraday's law, which we all know. And that's how you arrive upon a dynamical equation for the magnetic field. So you have two terms. This is known as the advective term, and this is the resistive term. The advective term is the one which kind of carries the field around, does various things to it. Basically, it's the effect of the flow on the field. What does the flow do to the field? And this is the term which is akin to the viscous term in your momentum equation, which you might have done. I think you should have done momentum equation by now. So basically, this is responsible for destruction of the magnetic field, right? So if you take the ratio of these two terms, then you get what's known as magnetic Reynolds number. It's analogous to your fluid's Reynolds number. Eta is replaced, sorry, the viscosity is replaced by this resistivity or diffusivity. Okay. Yes, so here's the beloved momentum equation that you must have come across by now already. I'm assuming things, but I suppose this is a correct assumption, right? Can somebody tell me that? In the chat, maybe. Okay. All right. If you've not done it, you will probably do it at some point. It's basically the equation for the flow, the velocity field, and you can get this basically from conservation of momentum flux. So this is the kind of equation that you would get on, and if the right hand side was basically zero, that would be a conservation equation without any sources or sinks. But once you have all these things on the right hand side, that means that you're putting some energy into the flow, or you're taking out energy from the flow, either of the two things, right? So this is a pressure term, which is related to how the thermodynamics of the system is going on. And this is the new which comes on introduction of the magnetic field. Basically, the current cross the magnetic field. This is known as the Lorentz force. And this is the main term which is going to feed back on the flow once you have the magnetic field, right? Viscous term, typically it's going to be the same form as what you saw in the induction equation, something like mu del square V. And this small f is anything else like body forces, or if you were injecting some energy via whatever violent processes that are taking place in the system, right? So I just told you that you need turbulence to be able to have dynamo action. So the question is, what are the sources of turbulence in different astrophysics? So in planets and stars, you have convection, and then in galaxies, you have basically these supernovae going off and stirring up the system. And in accretion disks, there's something called magnetorotational instability that also stirs up the fluid and creates turbulence. In galaxy clusters, you can have galaxy mergers. One thing that I want you to note right away is that the magnetic Reynolds number that I talked about, just introduced just 2 slides ago, is really large for all of these systems, right? So it's crazy large, right? 10 to the power of 19, 10, 29, but also in the sun, it's 10 to the 6. So it's really huge, right? So this is going to be like a sticky point, or it's not a sticky point, it's a very important point, because basically dictate the dynamics of the system, right? So now here I've written that the dynamo problem in sun, stars, galaxies is different compared to Earth, mainly because Earth has doesn't have as large Reynolds number as the sun, galaxy, etc. So it's kind of different over there. The RM is not that important. Okay, so now I want to give you like a physical picture of how dynamos work, right? Here on the left-hand side, basically, if you take a disk of plasma, so something like your galaxy, right? And suppose there was this magnetic field line threading through the galaxy. Typically, the galaxy will have something called the differential rotation. At different radius, you have different rates of rotation. So what happens is as it's rotating, there's shearing action, and because of that, the magnetic lines get pulled out, stretched out in the shearing action, and it gives rise to a field component in the plane of the disk, right? So you have essentially taken a straight magnetic field or magnetic field in the vertical direction and put it on the plane. And the question is there a process which can then do the opposite, right? So this schematic shows how that can happen. So in the disk, basically, I've been telling you that there's turbulent motion in the plasma, and what can happen is these turbulent motions can be helical in nature. And if they're helical, like if you can imagine small eddies, which are rotating like that in helical motions, then they can pick up the magnetic field in the plane and twist them up and bring them out into the poloidal, into the vertical direction, right? So, okay, yeah, into the vertical direction, right? So then that is reinforcing the magnetic field back uh, in the vertical plane. So this you can see is sort of a self-sustaining process. So this can happen. So it is like an instability, right? So you pull out the magnetic field in the plane, and then the motions then bring it out into the vertical direction again. So that converting the kinetic energy of the differential rotation, the kinetic energy in the helical motions to magnetic energy again. So this kind of self-sustaining process is what is going to give you the dynamo action, especially the large-scale dynamo, right? So now let me briefly tell you like some of the highlights of this research that happens on dynamos. Basically, dynamo is a theory that we want to understand, develop, and in order to understand the origin of large-scale fields. Now, the key thing is that what is the growth rate involved in these processes, right? And what is its dependence on uh, the key parameter, the magnetic Reynolds number. So Weinstein and Zeldovich in 1972, they basically conceptualized the idea of fast dynamos. The idea is that the growth rate shouldn't be depending on the magnetic Reynolds number, because imagine if the growth rate did depend on the magnetic Reynolds number, then because these numbers are really large, the growth rate is probably going to shut down, right? The growth rate is going to go down with Reynolds number. Remember, the Reynolds number is basically it's basically going to characterize how much of destruction of the magnetic field is taking place. So large Reynolds number means that very small destruction is taking place, and it turns out that that is an important thing, because if you want to do things to the magnetic field, but if you cannot destroy it at a sufficiently high rate, then you can't really pull and push the magnetic field around as much as you would like. I mean, it's not as simplistic as this, but the idea is that we don't want the growth rate to basically depend on, really some parameter which is like really large. So then, of course, it was soon discovered that, the steady flows do not really give you fast dynamos. You need to have random properties or chaotic properties associated with the flows. They need to be turbulent. And once you have these turbulent flows, they can give rise to fast dynamos. So there have been a lot of studies of dynamos. So when I say kinematic, what I mean is when the Lorentz force is not important. Force that I told you is sitting in the momentum equation that's feeding back on the flow. If that is unimportant, which initially it would be unimportant while the field is growing from really small values, because the field is still very weak to back react on the flow, during that time it's still growing. So the earlier studies, which I mean, we always start with the linear problem, right? We want to do the nice simpler linear problem first. So we want to just see and observe that this particular equation that I introduced a few slides ago, the induction equation, right? That is basically linear in B. You can see that. So there's like one operator which is acting on B. So if you didn't worry about, coupling it with the momentum equation, you can simply solve this equation standalone. So lots of people kept doing that, and it was not like a very straightforward problem, and it's taken a really long time to have even consensus over the answers for these problems. So I've highlighted some of these names, maybe familiar to you. Steve Tobias is in the applied math department, also David Hughes. They've all worked on this stuff. Yeah, so this stuff has been going on, but nowadays people have gone on to, look at the nonlinear problem. That is, once field grows and it saturates, what happens then? And there are questions associated with it, right? So one of the theories that's been the cornerstone theory is known as the mean field theory. You might have heard it in the context of turbulence as well, where you basically filtering out magnetic fields and velocity fields as large scale and small scale. You're taking mean and fluctuations. Once you do that, you get what is known as the closure problem. and that is another huge field by itself. Right. So mean field theory is used to study magnetic field evolution as well. Right. So now I am going to tell you about the work that I have done in this area. Right. So at Leeds, we were trying to answer these questions. There's still some sort of ongoing stuff, but I'm probably going to write a paper pretty soon. Questions we were trying to address was that, does the large-scale dynamo generation depend on magnetic Reynolds number? I told you that that was an important thing, right? Then, so what happens to systematic or large-scale fields in the nonlinear regime? And the thing is, a lot of these studies have happened in closed system. By closed system, I'm usually a lot of people like do these studies. I mean, to initially kind of conceptually understand stuff, you do these idealized simulations where you have this closed system which does not interact with with outside. So it's sort of slightly artificial because all your astrophysical systems are really open systems, even though the sun is like a gravity bound object and so on, it's constantly throwing out stuff or things like that. So that kind of stuff can happen. There can be winds from, or there can be feedback from the, I don't know, from neighboring objects and so on. So most astrophysical systems are open systems. So we are trying to understand what happens when you go from closed to open, right? Then also an important quantity in the study of dynamos is what is known as magnetic helicity. So I've already told you that the fluid needs to have helical motions to be able to, get conversion from one component to another component of the field, right? So I kind of showed you that earlier on. Um, so magnetic helicity, so due to this kinetic helicity, what happens is you induce helicity also in the magnetic field, and then when you induce helicity in the magnetic field, that has certain properties because it's now a topological quantity, and you can try to understand what's going on by studying in particular the helicity that is induced in the system by the flow, right? Induced in the magnetic field by the flow. So these are kind of the general questions that we are asking. So, right. So what I have done is to run simulations where I basically design the simulation, like uh, what kind of system I want to study, and what kind of model equations, what kind of boundary conditions, initial conditions, and so on. So I'm going to just briefly do all of that. So the model I have here is your momentum equation, as I showed you earlier on. And okay, I seem to have included also shear, but that's not actually true. There is no shear in my system. This F over here is the only seemingly unknown thing. So that's basically the Galloway-Proctor flow-based forcing. Don't worry about what it is. Basically, I'm injecting energy into the flow to generate turbulence. And this is nothing but the induction equation, but in the uncurled form. So you can always write down the magnetic field as curl of the vector potential. You might have done this in your electromagnetism classes. So this is the vector potential. So if you unleash the magnetic field equation, you get this equation, and then there is something about gauge problem, but don't worry about it. If you have particular questions, you can ask me if you know already the intricacies of gauge. Right. So the simulation setup. So I have run simulations at 3 different resolutions. Uh, 64 cross 64 cross 32, 128 cross 128 cross 64, 256 cross 256 cross 128. So it's basically this box which has uh, so many grid points in certain directions, and only half of them in the third one. That's because in the third direction is it's not as important as the 2 other directions. The Galloway forcing has certain properties, so we are taking advantage of that, and reducing the number in the third direction. Um, yeah, so this leads to, Reynolds numbers of 150, 300, and 600. You can see how ridiculously low these numbers are compared to the astrophysical systems that we have. So these numbers are never going to be sufficient. I think maybe even 10 years down the line, I don't know if we are going to ever get there. Like, to get like 10 to the power of 6 is amazingly difficult. But anyway, so we do with what we have. Um, I have already introduced Reynolds number to you. So this is the forcing wave number. So I'm forcing the fluid at a certain scale and putting the energy at a certain scale, so that I can observe certain wave, or the magnetic field which grows on scales larger than this scale, right? I have to, if I'm forcing at already k equal to 1, which is the largest scale in the box, right? Then I don't I don't have scales to observe the large scale field at, so I have to keep the separation between large and small pretty large. So my small is as small as 9, right? So the 2 types of boundary conditions that we have employed are periodic and this other one. So the periodic boundaries, so periodic boundaries on every direction essentially means that you have closed out the system, right? But once you have something else, some non-trivial thing, you have made the system open. So in Y, in another set of simulations, I have basically done this, employed this boundary condition, where basically you have stress-free condition for the fluid, the flow, and for the field, it's something called the vertical field boundary condition, right? Um, so this is basically the field is sticking out vertically without the horizontal components. So this is what it translates to. Though I have given in terms of vector potential, if you translate it to the magnetic field, that's what it means. Okay. So the initial condition is basically giving weak random fields that the dynamo can then amplify it and grow it. Then the velocity field is initially 0, but you're forcing will put in the energy and make it turbulent and so on. So the code that I've used is called the Daedalus code. So very nice one which has been developed fairly recently in recent years. But of course, maybe it's already now 10 years ago or something. Yeah. So this code is written in Python along with C++. It's basically it's a nice one. It's a flexible framework to solve differential equations, and this is what makes it nice, because basically you can solve any. I mean, it's not like the equations are hard coded, or you can basically put in just some passive scalar equations, or if you don't want magnetic fields, throw it out or whatever. So you can use this code to solve any set of differential equations. So that's what's nice. So do go and check it out if you want, because I think like a lot of you are going to do numerical stuff in the future. So to play around with, you can install it on your laptops even and run stuff like that. So yeah, so I use this code, and I've used the the Leeds ARC4 cluster, so the basically high performance clusters to run my simulations. Right, so the two sets of simulations are with periodic boundaries and non-periodic and so on. So yes, so I wanted to show you a movie of the dynamo simulation. So I kind of now will go back and to the screen sharing mode. I can show you the movie. So here's the movie. So initially you see basically nothing because everything is very weak and small in strength. Eventually you can see some sort of chaotic motions. This is basically the flow going swishing around, and you can see the field is slowly gathering strength, and as it is gathering strength, it is coming out in a certain pattern, right? And you can see this very large scale pattern on the scale of the box even, right? So you have these fields which basically the dynamo in there has. I'm going to play this movie again. Uh, yeah, so basically the flow is moving around. It's turbulent, and you would think that such a turbulent system will never give you an ordered anything very ordered, right? But eventually, you see these really large scale fields coming up on the scale of the system. I mean, this is pretty cool, and this is large scale dynamo in action, right? Okay. Let me now come back. Okay, I've been talking continuously, so I'm just going to drink some water if you don't mind. Right. So I told you earlier about mean field theory and how that is the most commonly used framework to analyze dynamos. So these are the mean field equation. This is the mean field equation. So this bar on top of it is basically referring to a mean field or a large scale field, which is kind of turned out field or something. So this is basically an equation for the filtered out field. It's not very different from the induction equation that you've seen earlier, but it's got uh, some new stuff. It's not u cross b anymore. You see, there's something alpha, and the dynamo that I showed you in relation just now is known as the alpha square dynamo. So what is this alpha? So this alpha is famously known as the alpha effect. Um, you may, I mean, remember that the helical motions twist up the magnetic field, and so on to bring it into the poloidal or the vertical plane. That phenomena, the physical phenomena, is encapsulated in this alpha, and many a times people just refer to that physical phenomena as the alpha effect, right? So in my forcing was such that there were helical motions in the flow. So I mean, you could have asked me, like, how are you making sure your simulations are going to give you a dynamo? I mean, can you just have turbulence and that's it? Can you have dynamo? No, you need to have this ingredient, the kinetic helicity in the turbulence. If you don't have helicity in the turbulence, then you will not get a large scale dynamo. So so this alpha encapsulates that the kinetic helicity and so on. So if you were to solve these equations, by assuming standard linear stability calculations. Then you get something called the Beltrami modes. Okay. So these are Beltrami modes. I mean, basically it's either something in Z, X, or Y, right? Km being the wave number at which the mean field resides. And what is very special about Beltrami modes are they are force-free modes. But okay, I will not go into this at present. We will see if we have to encounter this property of it later. But yeah, okay, so if I take my simulation box and I do the averaging that is necessary to see the large scale field. So what I have done is, we done some sort of planar averages. So in this case, I have, okay, in this left panel, left set of panels, what I've done is planar averaging. That is, I've averaged out the magnetic field on xz plane to 1D vector along y. Okay, and that 1D vector I plotted as a time series. I mean, like, how does the 1D array evolve? So this is Bx component, By, Bz. So I've also put a bar on top of Bx, which means that this is the mean field that I'm talking about because I've done this averaging, right? So it turns out that the Bx and Bz components have large scale fields, whereas By doesn't show anything. And this is for the Reynolds number 150 case. But if I go to other Reynolds number, we see different kind of stuff in the sense that instead of By being 0, Bz is 0. So this is essentially the Beltrami solution. Do you see that? So what's happening is that when the large scale field arises, it randomly chooses to align itself along, I mean, to vary along either of the three directions. So in case of the 150 Rm, by Rm I mean the magnetic Reynolds number. So in the 150 Rm case, the field is varying along Y. But in the 300 case, it is varying along Z, and also in the case of RM 600. It just randomly chooses so because it just has to break the symmetry. It's like spontaneously breaking the symmetry and just aligning. I mean, choosing one particular direction to vary along. Okay, so these are basically the Beltrami solutions which I just presented to you in previous slide, right? So this is like cos and this is sine. This is again cos, sine, minus sine, I suppose. Sine, cos. Yeah, so this is the kind of the simplest stuff that you can get, you know, a closed idealized box simulation where we are trying to study the magnetic field generation. So this is the simplest kind of solutions that you can get uh, given that you have helical forcing. So this is the closed system. This is all kind of really well-known stuff. Now I have to also do the open, like if I vary the boundary condition, like if I have one of them as an open boundary, then what happens, right? So that is shown in this encapsulated in this uh, space-time plots. They look fairly similar to the previous one, but note a significant difference. I'll tell you all, I'll point out the differences. One is that the By component is always 0. This simply comes from the fact that in the y direction, the system is open and non-periodic, and that criterion alone is sufficient. Itself imposes brings out this kind of solution where By is going to be 0. Here again, you may say that, oh, this seems very similar to probably what we saw in the closed system, but it's really not. These are not Beltramic solutions, because it turns out that the boundary conditions are such that these fields need to have certain properties. That is, they need to be non uh, antisymmetric around y equals 0 on. So even though they look fairly similar, to be even slightly antisymmetric is enough. Here they look nearly antisymmetric, but here you can see that uh, there's like a lopsidedness and so on. So yeah, so with non-periodic case, this is the kind of solutions that we get. So now we can make these plots of how the field is growing in totality. Like if I take these solutions that I've done and take the RMS value of the 1D array and then plot it as a time series, then how does that look like? So this is how it looks like. So you can see that this is the growing phase, like any stability kind of growing, and it grows exponentially. Right? That is what is the fast dynamo if it grows exponentially, right? But actually, it's not yet there, because what happens is it eventually slows down, and you can see that as you increase the Reynolds number from 150 to 600, if you increase the Reynolds number, it's kind of slowing down. So this is a problem, because if you see astrophysical systems are largely really high Reynolds number. So if I were to do simulation for the galaxy, very, very high Reynolds number, this is like really going to like bring this thing down, right? So it means that you are not going to hit your required amplitude levels or significant field strengths if you have really large RM. This is not good. So my experiment with opening one of the boundaries was to see if that manages to relax kind of behavior or change it altogether. It doesn't change it altogether, but there seems to be a little bit of difference. I mean, there still seems to be this kind of slowing down, but that slowing down is happening a bit later as opposed to a bit earlier. But these are again something that's still under needs to be studied much more robustly, because this is only one kind of boundary condition that I have played with. You can do other things and see what happens. But the one crucial difference between the periodic case and the open boundary case is that though here I plotted the mean field strength to the total field strength, right? If I would plot the mean field strength to the total energy available in the box or in the system, then it means that actually in the closed domain case, the field strengths that are achieved are actually much higher than in the open case. This is much higher in the sense, okay, it's maybe a factor of 5 higher than. So somehow by opening the box, we have managed to actually reduce the amplitude of the large scale field, it seems. So that is also worrisome. And this kind of stuff is can be understood if we actually study what is known as magnetic helicity. So I had bunch of slides to talk about helicity, but I think I'm already going to stop at this point, so that I give you for questions if you have any questions. But if you don't have any questions, I can talk about magnetic helicity for some more time. What do you want to do? Actually, I didn't even come to reconnection, so I think I overestimated and I was overambitious to talk about both dynamos and reconnection. But if you want me to tell you about reconnection, I can do that also. Um, okay, so maybe I would like some kind of feedback from you guys in the sense that is there something that I could explain better? Do you have any questions? And if you want, you can raise your hand, and I can take the questions.
I was just asking if you could show the first video again. I think it was the magnetic reconnection to the Earth or something, because it was going quite fast, so it was hard to follow for me anyway.
Ah, okay. You mean the video in which I talked about reconnection and what's going on? So what's going on is at this point, you can see these magnetic field lines, which have emerged out of the sun's surface. So what happens is that, due to buoyancy, these field lines which tend to come out, protrude out of the magnetic field surface. And as they are doing so, they're carrying plasma with them, okay? So you can't really see the plasma. It's just a schematic thing. So that's what this is. So as they come out, um, you can see this kind of pinching off. So I mean, here it doesn't look like much, but what typically happens on the surface of the sun is that because the foot points are moving for these magnetic field lines, tend to twist and turn and so on. So when they're twisting and turning, they kind of get entangled, and in this entanglement, the magnetic field lines interact with each other at this point, the pinching off point, and then what happens is reconnection takes over, and so reconnection is wherein oppositely directed field lines come together and reconnect, and then they move out of the reconnect domain from the perpendicular direction. So the pinching off throws away this entire plasma out. Okay, and further this stuff travels towards Earth, and Earth's magnetic field interacts with it. Again, note that the magnetic field lines at the point of interaction are oppositely directed to each other, right? When this is so, then magnetic reconnection can take place, right? And this reconnection allows for the field lines to sort of come out in the direction opposite in the opposite direction of that facing the sun, and this tends to actually form shocks, and then again it does another set of reconnections, and as it is doing so, the plasma that is available in those field lines travels along the magnetic field lines of the Earth to reach the poles, and then give rise to these beautiful aurorae. That's basically what the aurorae. What's happening over there is that there are these charged particles, right? Field lines for holding. Uh, those interact with the atmosphere and give rise to these all these light stuff that comes across as aurorae, right?